Today we're going to talk about Lagrangian mechanics. So what is Lagrangian mechanics? So Lagrangian mechanics is another way of understanding a motion, how to derive the equation for motion. Instead of using force, says such as tension force, y-axis force, x-axis force of gravity, instead of calculating every vector forces, what we're going to do here is use just only kinetic energy and potential energy and use those things in order to derive our new equation for motion for that specific object. So here we have the Lagrangian. It's going to be L is equals to kinetic energy minus potential energy, and we also have these partial differential equations, and this is going to be the equation of motion in Lagrangian mechanics. This is how in Lagrangian mechanics we define force is equals to mass times acceleration, because that is what we know in classical mechanics, that is force is equals to mass times acceleration. But in Lagrangian mechanics we use partial differential equations in order to in order to represent the equation of motion. Okay, so x here is an x dot. So x represents the position, and x dot is going to be the representation for velocity. So we use not generated, but general coordinates. It's the generated coordinates. I don't know what they call. So we're going to let v is equals to x dot and the y, which is going to be x. So, and in Lagrangian mechanics is more efficient way to approach Newtonian mechanics. This is essential, or this is more useful in complex classical mechanics problems. If we do have a lot of forces that is acting to an object, then we cannot use the old way, which is going to be Newtonian mechanics. So we're going to use Lagrangian mechanics. So Lagrangian mechanics, it is used to derive the equation of motion just using kinetic energy and potential energy. It's just energy. So Lagrangian mechanics is free requisite for quantum mechanics. So this is really essential if we're going to take quantum mechanics. We need to go into Lagrangian mechanics first. So now we know the definition. Let's try this one. Let's say we have a mass and it's going to be uh, moving downward because the influence of gravity, and we have a length which is going to be y. It's going to be the height, I mean. So what we're going to do here is we're going to let y is equals to x. So we're just going to use generated or generalized coordinates, and v squared, we're just going to make it as x dot, because the derivative of position with respect to time is going to be dx over dt, and that is another way of representing the derivative. So it's going to be x dot. Now we know the kinetic energy and the potential energy here. It's going to be 1/2 m velocity squared, and the potential energy is mg times x. So what we're going to do is plug it into the Lagrangian equation here. So we have this. So after we have that, what we're going to do is take its partial derivative with respect to x, or we can just take the partial derivative of the Lagrangian with respect to x dot. So for me, let's start first with the partial derivative of the Lagrangian with respect to x. So that's going to be partial derivative of L with respect to x is equal to negative mg So that's the first equation. Now let's take the partial derivative of L with respect to x dot. So this is going to be mx dot. So now we have this. So if we do have that now, what we can do now is take its derivative with respect to time. So that's going to be d over dt. Going to take the derivative of both sides with respect to time. So here, this is going to be look like a derivative with respect to time of the partial derivative of L with respect to x dot. It's going to be m times x double dot. So x double dot, that's going to be the acceleration, because the second derivative of position is going to be acceleration. So now we do have what we need. So what we can in Lagrangian mechanics. So let's flag it this. So after we flag it in, we can know for sure what's going to be the equation of motion here. What is going to be the acting force of this in this particular problem. So we have this. We can just divide this by m, leaving at us with x dot double dot minus g is equal to 0. Actually, we're wrong here. We need to make it as addition. So let me replace the sign here, and we have a negative sign here. So x double dot, we know that's going to be the acceleration. So the acting force here, the equation of motion, which is not really an equation, is going to be negative 9.8 meters per second squared, which is true.